Good afternoon, students. Let us start the lab class for today. In the previous lab class, we had discussed about the basic introduction about the Xylink software and how simulation and synthesis is possible using the Xylink software. And I had discussed some basic differences between VHDL and Verilog. And I had shown you the snapshots of the initial working of the Xylink software. So from today, let us start with the experiments. Today, let me discuss the experiment number 1, that is write an HDL code to realize all logic gates. So to write an HDL code to realize all logic gates is the aim, then synthesize and view the Rtl schematic also. I will tell you about what is meant by Rtl later on. So the software required is Xilinx 12.1 Isim simulator. Right now in my laptop, I have Xilinx 14 version, and later on I am going to show you the demo also. The minimum requirement here is Xilinx 12. If you have a higher version, then that is appreciated. So digital systems are said to be constructed by using logic gates. These gates are AND, OR, NOT, NAND, NOR, XOR, XNOR gates. The basic operations are described in the truth table here. You already know about the truth table of all these logic gates. Let me show you the first VHDL program. Now in the VHDL program, the very first statement is library IEEE. I had told you even in the last class that VHDL supports even external libraries, external packages. And in library IEEE, we use this particular package for today's experiment, that is use IEEE.std_logic_1164.all. This particular package contains all the logic definitions that are required for an electronic hardware. Now initially in VHDL we will have a block called entity, then we will have a block called architecture. So you can see entity gates is, the name of the entity is gate. Sorry, power went off here, so I have connected to hotspot now. There has been a frequent power cut in our area today. I think now you are able to hear me. Wait until these problems are resolved. Don't keep on sending me messages because that is interrupting me. I hope now you are able to listen to me. So I have told about this entity. So entity gates is port A, B, that is the input ports, and C, D, E, F, G, H, I output ports. As you already know, it was discussed in the theory class also, that the standard underscore logic means these ports A and B can have 9 values. If this is not specified, then we have to declare them as in and then bit, and bit can have only 0 and 1 values. So this is about entity. Then you can see in the architecture G1 of gates is, which means for the entity gates, we are declaring one particular architecture called G1. And you know that there can be multiple architectures defined for a single entity also, depending upon the requirement of the project. Whereas in all our lab experiments, we will not have multiple architectures because we are conducting only smaller experiments here. So architecture G1 of gate C is then begin. C is assigned to not A, D is assigned to A or B, E is assigned to A nor B, F is assigned to A and B, G is assigned to A NAND B, H is assigned to A XOR B, and I is assigned to A Xnor B. And then we have to end the architecture. So this is a simple VHDL program where we are defining only the logic gates. Now you should remember that this particular symbol is the assignment operator in VHDL. Now for the same thing, you have to generate a test bench code. Later on I will show you the test bench code generated by the Xilinx software. And there in the VHDL program, you'll have to remove all the clock definitions, because by default, VHDL generates the clock definitions also inside the test bench. But as we don't require it for the logic gates, you have to remove it. Whereas Verilog is slightly different. In Verilog, by default, the clock definitions are not included in the test bench. We only have to manually add it. So these are the differences between, again, VHDL and Verilog. So you can see the test bench code VHDL. Here A is assigned with the value 0, B is assigned with the value 1, then wait for 100 nanoseconds. Later on, after 100 nanoseconds, A is assigned with the other values 10, 11 and 00. This is the test bench code for VHDL. Let me continue with the Verilog program now. Verilog program is also a very simple program. You can see here module, gates, and this is the port list which we have to specify in Verilog, because there is no entity and architecture separation here. And it is necessary that in Verilog, in the beginning itself, all the ports are specified, because this module can be utilized by another module also in Verilog. So module gates A, B, C, D, E, F, G, H, I, then input A, B, output C, D, E, F, G, H, I. Now you can see this keyword assign. Assign, C is assigned to not of A. You can see that in Verilog we are using this symbol tilde for not. Similarly, the symbol pipe for or. We are using the symbol ampersand for and. We are using the symbol caret for XOR. Now you can see here, as this whole program is a concurrent execution, in Verilog we have basically two types of assignments called concurrent assignment and sequential assignment. Concurrent assignment happens always immediately, just like that, parallelly. Whereas sequential assignment happens inside a sequential execution wherever we have a keyword always or initial. And then again, inside that sequential assignment, we have a non-blocking assignment and a blocking assignment. So in that way, you remember, more details about these will be shown in examples in the theory classes only. But remember that even in VHDL also such assignments are there. But in VHDL such distinction is not there when we write the code, because VHDL automatically has a support. And VHDL is much vaster than Verilog. In that way, VHDL will exactly understand, so to say, about those assignments, whereas Verilog is a smaller language when compared to VHDL. So while writing Verilog code, the designers have to be really very careful about all these needs or necessities of coding. So you can see whenever we use this keyword called assign, then it is a concurrent assignment. Here in VHDL, we did not tell anything like that, right? We directly gave C assigned to not of A, because the code itself or the VHDL simulator itself will understand that this is concurrent execution. Whereas if we do not give this keyword assign, then the Verilog simulator an error. Verilog compiler itself will give an error. Later on, I will show you how the error we don't give the keyword assignment or assign itself. Okay, so in this way, this is a concurrent assignment. We will not have any sequential assignment here in today's experiment because we are dealing with the combinational logic only. As you already know, all combination logic are having a concurrent execution, means as soon as an input changes, instantaneously the output changes, except for the propagation delay of the gates, output immediately changes. That is called concurrent execution. Whereas in sequential execution, it is timed either to a reset signal or to a clock signal, and only when that particular event occurs, at that time only the output is going to change. Otherwise, the output is not going to change in the case of a sequential circuit. So in this way, as today's experiment is only logic gates, this is basically a concurrent execution because it is simply a combination of logic. Now, the test bench code for Verilog is wherever that add stimulus here is coming in the test bench, then we are going to give the values a equals 0, b equals 1, hash 100. A is assigned with 0, b is assigned with 1 and hash 100. You can see the differences here. VHDL uses a single quote for a bit and a double quote for a collection of bits. Whereas Verilog directly takes the value 0 and 1. These are some minor distinctions between VHDL and Verilog. And there in VHDL, we give the statement wait for 100 nanosecond. Here we simply give hash 100, which indicates this hash or cross hash symbol itself indicates that it is a time delay. So in this way, you can see how test bench code can be or stimulus can be given in Verilog. Now, results and simulation output, the HDL code for basic gates has been written and verified using test bench. I will show you the sample waveform which is there in the manual here now. Later on, I will actually simulate the code and show it to you. So you can see this is the output, simulated output, where you can see A and B are initially 0, 0. Then A is 0, B is 1. Then A is 1, B is 0. Next A is 1, B is 1. Next it has remained 0, 0. You can see that every 100 nanosecond the stimulus has changed. You can see from 0 nanosecond to 100 nanosecond, A and B value remained, then value is changed. And accordingly, the outputs are C, D, E, F, G, H, I, all the logic gates. So, what is this? C is not of A. You can verify this here. C is not of A. Whenever A is 0, C is 1. Whenever A is 1, C is 0. Again, A is 0, C is 1. Accordingly, all other logic gates are simulated and the output is shown. Now, what is RTL schematic? Let me tell you a little bit about what is RTL. RTL stands for Register Transfer Level. Sometimes people also use Register Transfer Language. RTL and HDL both are one and the same. But I'll tell you one statement or sentence, you will have to remember it lifelong. RTL is always HDL, but HDL need not be always RTL. Please remember this. RTL always is HDL, hardware description language, whereas HDL need not always be RTL. Now you may wonder what may be this. I'll tell you the answer. When we use HDL, hardware description language, we are actually using this HDL for writing a code and for implementing a hardware. Now, when we use this HDL only for simulation, there is no physical hardware or there is no physical circuit also. We are simply converting this particular code Actually, we are using a particular Verilog code. We are not actually converting. We are using this particular Verilog code for verifying the functionality of the code. But only when we perform a process called synthesis, at that time, the code is going to be converted into a circuit diagram. And only the code that is going to be converted into a circuit diagram, only that is useful for us. If any code cannot be converted into circuit diagram, that is of no use for us, because ultimately the circuit diagram itself is the hardware. Circuit diagram is the diagrammatic representation of the physical hardware, and the hardware is going to be implemented either on an FPGA chip or it is going to be manufactured as an ASIC. So non-synthesized HDL is a waste for us as far as manufacture is concerned. But non-synthesized HDL is required for us to verify whether the code is working or not, to verify the functionality. So whatever you saw right now, this is the simulated output. In the sense, without actually getting the code implemented on a chip or FPGA, we have simulated the code and we have verified. That means code is going to be mapped into the hardware, that we are sure. But right now synthesis has not happened and the code is not converted into hardware. That process is called synthesis. Last time I mentioned about two things called Isim and Xst. Isim means integrated simulator, which is only going to check the functionality of the code, whereas Xst is the xylene synthesis technology going to convert the code into the circuit diagram, and finally the circuit diagram will have a net list or network list, which is a list of all the nodes and components that are present in the circuit diagram, and finally that net list is going to be implemented on an FPGA. Okay. So what is RTL? Register transfer level. And what is HDL? Hardware description language. And what I told? All RTL has to be HDL. All HDL need not be RTL. Now let me ask a question to students who are listening to me. You already know that simulation is verification of the functionality of the code, whereas synthesis is converting the code into the circuit diagram. So now for simulation, we require a test bench, because in the test bench, we give the values to the inputs. Then we verify the states of the outputs. My question to you is, for synthesis, test bench required? Can anybody answer? I'll repeat the question. For synthesis, is test bench required? Is my question. Afterwards only I am going to discuss more about what is meant by RTL. Any answers? Okay, one student answered me that no, it is not required. That's right. For synthesis, test bench is not required. Why? Xnor Gate. So, for the case of synthesis, test bench is not necessary. Test bench is there only for our purpose to verify that the code which we have written is functionally all right or it is working. For that purpose only we require test bench. And for synthesis, test bench is not required. Yeah, there is an answer here again that it depends only on the construction. Correct. This code is going to be converted into a hardware. So this Verilog code is the main module which is going to be directly converted into a hardware. There is no need of giving an input and testing it as such during synthesis or after synthesis. But the point is, before synthesis, we should ensure that the code is actually working as per the logic. That is test bench. We require the test bench to verify that the code is logically accurate, because the synthesis tool will never verify the logic of the circuit. Please remember this. In Xilinx, we have two different tools now. One is a simulation tool, one is a synthesizer tool. Simulating tool will only check the syntax of the code, then it will apply the inputs as per given in the test bench, and it will simply plot the output using a GUI, graphical user interface. That's all. It is we who have to actually verify whether the logic is working or not. It is the designer who is verifying whether the logic is working or not. Similarly, the synthesizer tool is not going to worry about the logic at all. Whatever code you give, code is directly going to be converted into hardware, because it automatically understands this tilde symbol means NOT gate, pipe symbol means OR gate, and ampersand symbol means AND gate, caret symbol means XOR gate. Accordingly, you only have given which are the inputs, which are the outputs. That way, it will plot the circuit diagram for this particular code, and then it can be downloaded into FPGA. So this was the answer for my first question. Now my second question is, online today. That is why there are enough network issues today. Since morning we had enough network issues. So I hope now this network problem is solved. I hope it is working now. So what is RTL? Register transfer level. What is the meaning of that register transfer level? Register means what? Regist. Gist means something which is proved or something which is truth or summary. In generally, the word gist means summary. Regist means what? Whatever is the summary that is stored there. In general, register means some information that is stored. Whenever we have attendance register, it simply means the attendance of the students are recorded and stored in that particular register. That is what it means. So, in the digital electronic language, register means a memory element. Now, RTL stands for register transfer level, and some people call it as register transfer language also, which simply means corresponding to this tilde symbol, there must be a NOT gate existing in the library, right? This tilde symbol will be converted into a NOT gate. That means NOT gate must be already present in the FPGA, for example, or NOT gate must be present already with the Xilinx library. That means Xilinx should have a register, and all the codes, symbols or codes assignments will be transferred into the registers. That is the meaning of register transfer level. Pipe means OR gate, so OR gate must already be there in the Xilinx library. XOR gate must already be there in the Xilinx library. For that matter, whatever code we write, all that code must be converted into hardware, means all those hardware components as such must be present in the Xilinx library, at least the subcomponents, not all the components. All the logic gates which we use in that std underscore logic underscore 1164.all, they must be counterparts of a physical hardware that is present there, which means those are all saved in the registers. So register transfer level means this particular code is going to be transferred into those registers which are present in the Xilinx library. If that is there, then only it is converted into hardware. Otherwise, it cannot be converted to hardware. For example, if at all we write a code here, for that particular code, there is no counterpart in the registers in the software's library, then the hardware does not exist there. That is why I told you, non-synthesizable code is useless for us. If any code does not yield a circuit diagram, accordingly, it is useless for us, because ultimately we want a hardware out of the code. So that is why it is called as RTL. Now remember my statement, all RTL is HDL. All HDL need not be RTL. What do I mean now? All RTL is HDL, means all register transfer level must be hardware description language, because there is a corresponding hardware. But all HDL need not be RTL. This is my second question now. Can you tell me why did I tell all HDL need not be RTL? This is the second question. I'll elaborate this question now. We have written a main code, then we write a test bench. Now tell me, this main code is RTL. Is the test bench RTL? Is my question now. Test bench is definitely HDL. But is the test bench RTL? Think and tell me the answer. Test bench is not RTL. Tell me why. Main code is RTL, but test bench is not RTL. Tell me why. RTL deals only with the synthesis, whereas test bench is for simulation. Yeah, that is correct. Test bench is for simulation. For synthesis, we don't require test bench. That is fine. But test bench is HDL. Why is it not RTL? We are not using it during synthesis. That is fine. But why this test bench is not RTL? The answer is, you have this A equals 0, B equals 1 and hash 100. For this hash 100, there is no hardware. This hash means it is a delay, right? When we have this cross hash 100, that means 100 nanoseconds delay. For 100 nanoseconds delay, we do not have a hardware, right? Whenever we require a delay, we should have a counter, right? We should have some sequential circuit which can introduce such delay, right? But here in the simulation, we purposefully want a delay because we want to give this input. Then we have to wait for 100 nanoseconds and we want to verify the output. Then we go to the next input stimulus. So that way test bench code is a sequential executing code. Whereas even the main code can be sequential executing code in case of a flip-flop, in case of a counter. It can be a sequential executing code. That sequential execution has nothing to do with RTL or HDL. Sequential execution and concurrent execution are part of HDL. It can be part of RTL also. But the point here is, for this delay, there is no corresponding hardware at all. We have hardware. What? all logic gates are hardware, then all flip-flops are hardware, then all adders are hardware, multipliers are hardware. Adders and multipliers again are comprised of logic gates only. Flip-flops are again comprised of logic gates only. And counters will have flip-flops, registers will have flip-flops. That way we can keep on building up higher level electronic systems using the primitive circuit structures. But for delay, we do not have a direct hardware at all. Whenever delay is required, we should have a loop, for loop or while loop. We will have to implement a delay by writing a Verilog code. But in the test bench, we simply give the symbol hash, because the simulator will simply wait for 100 nanoseconds, then it will apply the next set of stimulus. So test bench code is containing something which cannot be synthesized. This hash cannot be synthesized. Delays cannot be synthesized. Wait statements cannot be synthesized, because for wait statements or for delays, there is no corresponding hardware. That is why test bench code is HDL. But test bench code is not RTL. Remember this. Test bench code is a hardware description language. But test bench code is not a register transfer level. Remember this. So I hope this point is understood. Any questions here, or shall I proceed? If you have any questions, you can ask me, or else I will proceed. Okay, if there are no questions, let me proceed now. You can see here Rtl schematic, and you can see here top there is this Manoj. One student called Manoj had made this project. That's why he has kept his name only Manoj. Below which you can see the chip number, that is the FPGA chip number. Below which you can see these gates G1. Whereas at the upper point, later on I will show you, it is not, that snapshot is not here for simulation. I will show you later on. You can see this synthesize XST and view Rtl schematic. Now this is what is the block diagram which Xilinx has developed, XST has developed. Xilinx synthesis technology has converted the code into a hardware where you can see A and B are 2 inputs and C, D, E, F, G, H, I are 7 outputs. Now this is the Rtl schematic, register transfer level schematic, means it has successfully converted the code into the hardware. Now when you conduct the experiment, when you double click on this particular block diagram, you will see all the gates there. Later on during the demo, I will show you that. So I think I will stop sharing this PDF now and let me show you the demo. Meanwhile, if you have any questions, you can ask me. So I hope you can see this now. You can see at the top, I have created a project for today's experiment called logic gates. And below which I have given the chip number. When I create the logic gates project itself, it will be taking that particular chip number in general. Actually, this chip number has to be corresponding to whichever chip we are going to use in our lab, where we are going to download the code. Below which I have written today's program. You can see this. This is Sorry, this is test bench. This is today's program. This is module gates ABCDFGHI and input AB, output CDFGHI, all the assignment statements and end module. This is the code. Now, once this code is completed, you can always input the code using this. See, you have this new text file and you can open that. It will open a blank screen, and on the blank screen, you can type the code. This is how you have to type the code. This is a regular editor, just like we have MS Word, we have Notepad. This is a built-in editor inside Xilinx. Let me close this now. So that is how I have typed today's code. And later on, what you have to do is, you can always right click on the chip. Remember, above is the project, below there is a chip, and then below there will be this code during simulation. Now because I have already simulated, you are seeing the test bench on top. And I had told you in the last class, test bench is always called as the top module. If you remember that, test bench is always called the top module because it is at the top and this is at the bottom. And test bench is going to give the stimuli to the main module, or UUT, unit under test. We also call it as design under test. So topmost we have logic gates. Sorry, logic gates is basically project. Below which we have chip, below which we have test bench, below which we have the main code. Now, whenever you want to insert a design for the chip or for the project, you can click on this new source. When you click on this new source, it is going to ask you these many options. All these options I had told you last time. What you have to do is click on this Verilog module. And then you can give a file name, then you can type the code. Or else, if you already have that code, you did not give a new source, you can simply give add source. Now, when you give add source, it is going to ask you the file which is already saved in the hard disk. See, I have already saved this file in the hard disk. That's why it is showing like this. Now, later on, you can select this particular file and you can click on behavioral check syntax. I'm just double clicking on behavioral check syntax. Now, this green tick mark is coming, and below it is showing process behavioral check syntax completed successfully. If there are errors in the code, it will show you. Now, just for the sake of today's class, let me remove this assign. I have removed that assign. Let me save it. Now, let me check syntax once again. See, it has shown behavioral check syntax failed, and it is showing the problem there. Problem is line 4 syntax error near equals line 4 C is an unknown type. Line
I think there's a network connection. Just stay in the meeting, all of you.
There has been lot of network error today. We will have to bear with this now. I hope it is visible now. If it is not visible, please let me know. Is it visible? Somebody should answer.
Yes, sir.
Is it visible? And am I audible? Yeah, I am audible. Okay, obviously. So you can see in line 4 it is showing syntax error near equals because in Verilog we have not declared any sequential execution here now, right? This is all concurrent execution because it's a combinational circuit now. So whenever we have a concurrent execution, Verilog expects that I should have one assign keyword here. If that assign keyword is not given, then it is thinking that it is a sequential execution. That is the complication with Verilog. That is where we should be careful. Now I am saving this again and let me check syntax once again. Now you can see this green tick mark has come. If the green tick mark has come means the code is syntactically fine. But I cannot simulate this code. See, I have connected this to logicgates.v. Now can I double click on the simulate? Just see here, I am simulating the code directly and process simulate has come here and something has come there. It has plotted the values, but all the values are blue, blue and red, red, red. What does it mean? It is all Z, Z and X, 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 X. X means unknown, Z means high impedance. A and B are high impedance, all other things are unknown. Can you tell me why this happened? Can anybody tell why this happened? I tried to simulate the Verilog code directly without the test bench, right? Even though test bench was present there. The code as such does not contain the values for A and B, right? Only the test bench contains the values for A and B. So if you try to simulate the code directly, it will not work. That's what I'm showing you here. Can't see the waveform window. Are you not able to see the waveform window? I have shared this screen. Okay. I am sharing the Xilinx. Let me stop sharing this and let me share that other one. Yeah, this one. So now you are seeing the waveform window, right? You can see here A and B are shown as ZZ and C till I are shown as XX and Z high impedance is shown in blue color in the GUI and X is shown in red color in the GUI. Now why this happened? Because the RTL, whatever we are going to simulate is basically RTL now. That RTL or the logic gates code does not contain the values for A and B. So the conclusion here is you cannot simulate the RTL code directly. You require a test bench always. You can synthesize the RTL code directly, but you cannot simulate the RTL code directly because test bench is another program which is containing the values for A and B. That is the idea. So let me close this. Let me stop sharing this and let me share once again the Xilinx navigator, project navigator. So here you are seeing this particular code. Now I try to simulate the code directly, which is not possible. That is why I am showing you the test bench now. Now you can see this is the test bench which is automatically generated by the Xilinx tool. You can see it's a lengthy test bench create date, today's date it is showing, design name, gates, module name, everything it is showing. All these are comments here. Then it is creating a module called logic gates underscore test and regabc. Rega because input both the input values need to be stored until the 100 nanosecond delay is over. And all the outputs are wire because they are all combinational outputs. Now gates UUT, this is called instantiation. I'll not tell you more about instantiation now in the lab class because in the theory class we are going to discuss more about it. But I'll tell you what is the meaning of instantiation. Meaning of instantiation means now you have in the main code you have all these NOT gate, AND gate, NOR gate which are defined. In the test bench, an instance of all these is required. Instantiate the unit under test. The instance of all these identifiers must be required. Here instance means it is like a photocopy which you take. For example, let us say I have a paper and that paper's photocopy I take. And that photocopy in general language we call it as copy number 1, copy number 2. But in the hardware description language we call it as instance number 1, instance number 2. Which means you can define one NOT gate in the library. In the library there will be only one NOT gates definition. But in your actual design you may require some 100 NOT gates or 200 NOT gates. Now all those 200 NOT gates are 200 instances of one NOT gate. That is called as instantiation. More about the process of instantiation will be discussed only in the theory classes, not in the lab class. So the test bench is going to instantiate the unit under test. Unit under test is our logic gates for today's class. Later on, you can see this keyword called initial. What is the difference between always and initial? Always is getting into an infinite loop where initial will work only once. In VHDL, we have a single keyword called process. Whereas in Verilog, we have these two keywords. One is called initial, one is called always. But today we have not used that keyword always in our program because our program is for logic gates. It is not a sequential circuit. In future, we are going to use the keyword always in our sequential circuit experiments. But test bench is always sequential, right? See, test bench till now was concurrent. Right from this statement module till this statement ending, this instantiation, until then this is concurrent. But now as soon as this keyword initial is there, you can see the word begin also. Means from now on it is going to be into a sequential execution. Because we have to give 0, 0, then wait for 100 nanosecond, again 0, 1, wait for 100 nanosecond. This is now a sequence. That is why we have to use a keyword initial. Why we are using initial? Why not always? The reason is when we simulate for 400 nanoseconds, we will give all these values. 100 nanoseconds each is one set of stimuli. And then we complete the 4 sequences. That's all. 0, 0, 0, 1, 1, 0, 1, 1. We don't have to go for a never-ending loop here. If at all we give always instead of initial here, then it will go for a never-ending loop. That is why test bench itself has given this word. I have not given this word. I have given only these 4 statements. Whatever I am highlighting, only these 4 statements I have typed here. Otherwise, everything else is automatically generated by the software. So initial keyword automatically comes, then begin comes, then A is 0, B is 0, initialization is done by the software itself. It is waiting for this 100 nanosecond here. Then it is telling me add stimulus here. Wherever it is telling add stimulus here, there I have added these 4 stimuli. Then automatically end and end module are there in the code. Only thing is, only these are the 4 statements which I have typed here. Okay. Now this is why it is using a keyword initial. Please understand all these basics thoroughly. Don't take all these concepts lightly because we are discussing EDA, electronic design automation. It may seem to be a little complicated for you in the beginning, but gradually when we keep on discussing the same thing again and again, it will become clearer to you. But they are all interrelated that way. So now this is the test bench where I have added the stimulus. Now I will check syntax again. Behavioral check syntax. It has come as green tick mark and behavioral check syntax completed successfully has come. Let me do something for the sake of curiosity. Instead of initial, let me type always here. What will happen? Given always. See that blue color is coming there. Means the tool has understood that it is a reserved keyword. You can see the blue color is the reserved keyword. Green color is the comments. The Xilinx software automatically makes a color that way. Now let me save this and let me check syntax. Now also check syntax completed successfully. Okay, that is fine. But when I simulate, I'll have a problem there. Let me change it now to initial again and let me show you the output later on. Let me do that once again. Now, anytime, whenever you change it, you will have to save it and you will have to check syntax once again. So now, check syntax completed successfully. Now, as I told you, we cannot simulate unit under a test. We have to simulate always the test bench. Test bench is called as the top module. And you have to select this one only. And you should remember, there is this side is implementation, this side is simulation. Implementation means it is part of synthesis where you are downloading into the FPGA. I will show it later on. Now we are doing simulation. So these are the two windows. So simulation, I will click on simulate behavioral model. Now it has plotted the output. Let me share that. I'll have to stop sharing this and let me share the GUI. Yeah, you can see here now. Now there is this button here. This particular button, it looks like a football or volleyball. This is zoom to full view. I will click on this. Now you can see the output. Initially, you can see A and B are at the bottom. Anytime you can drag them to the top also, no problem. You can play with all these things. But let me not show you the play today. A and B are at the bottom. Other things are at the top. A, B, now it is 0, 0. And you can see the outputs there. C is the inversion of A, right? So it is showing there. Now, AB 0, 0, then 0, 1, then 1, 0, then 1, 1. You can see this all. This is 0, 0, where you can see it has stopped. So this is how from the test bench the delays are included there, and this is the simulator now. Now let me share project navigator. So here see, I have changed this to always. Let me check behavioral check syntax because I have changed it. Now let me simulate behavioral model. It has plotted the output now. This window is appearing again and again. Yeah. Now I'll share this with you. You tell me what has gone wrong. Yeah, you can see this now. Now you tell me what has gone wrong. That initial I made it as always. And you tell me, look at this and remember the previous output. And tell me what might have happened. Can anybody tell me? Any answers?
Simulation is repeating again.
Yeah. Because we gave the keyword always, it is going back to the loop again and again and again based on the timings which we have given, and it is showing the outputs. Now all the outputs are correct. All the outputs are correct. Logically, it is all correct. Only thing is it is going into the loop again and again. Now we will be confused. As designers or as verifying people, we will be confused. So it is better that I leave it as it is in the test bench as initial itself, right? Let me share the Xilinx Navigator. So it is better that instead of always, let me use initial. So when I give initial, this whole loop is going to be executed only once. Let me save it. And let me check syntax once again. And let me simulate. It will keep asking me, do you want to close the application again and again? Because that GUI is a different tool, which is along with the Xilinx itself, but it opens in a new window. Now you can see, wait a minute, let it go up, then I'll click on that ball for zooming to full view. Actually, that WebEx header should go up. Yeah, it has gone up now. Now you can see that it has executed it only once until the stipulated time period that is there in the test bench. It has remained like that till 1000 nanoseconds. Here you can see it has remained 1 which is corresponding to the code there. So that way initially is going to help us. We can move this cursor wherever we want to move, and accordingly we can check the values. Okay, you can see whenever I move the cursor, you can see the value here. A is 00 and you can see the values. When I move the cursor here, you can see A is 0, B is 1 and the values have changed. Accordingly, you can move this cursor anywhere. Actually, you can have multiple cursors also here, through which you can verify the logics. Today for the logic gate, it is very easy to verify, nothing much. But if it is a bigger project, it is difficult. So if it is initial, it is easy for us to verify. That is the point there. That is why unable to see. You are unable to see. Let me share it once again. Okay, now I hope you are able to see. You can see this cursor. Whenever I move the cursor, you can see the values also changing. And when I move it here, you can see A has become A is 0, B is 1. Accordingly, it is going to change here also, here also. So that way we can easily verify the logic states of the outputs with respect to the inputs. Lastly, let me move on to show you the RTL or synthesis. Let me stop this GUI. And let me come back to sharing the Xilinx project navigator. So now, the last part of today's class, I am moving on to this implementation instead of stimulation. Simulation is verifying the functionality of the code now. When I move on to implementation, you can easily see there is only this gates, logic gates. The tool automatically separated the test bench because for synthesis, test bench is not necessary. Now come down below, you have this design utilities. In this design utilities, you have these, I have to select this now, gates, okay. Now you can see, here we have synthesize Xst. You should be selecting your main module here. That main module is this one only, logic gates only. Now come down to synthesize Xst. I will double click on synthesize Xst. Xst is Xilinx synthesis technology. As you know, I cannot synthesize the test bench. Why? Because test bench contains delay statements which are not synthesizable. That is why test bench is HDL. Test bench is not RTL. Synthesis takes a little time. Now process synthesize Xst completed successfully. Now I will expand this button, and below that you can see view RTL schematic, view technology schematic, and check syntax and generate post synthesis simulation model. We will not go to the other two. We will see the upper two now. And whatever is that implement design or generate programming file, configure target device, that we will not discuss in today's class. It is actually for the next part of our lab. Whenever you actually download the code into FPGA, that is where we require the next part called implement design, generate programming file, and configure target device. So let me show you the view RTL schematic now. Start with the Explorer wizard. Okay. Something else is there. Let me. Start with the schematic of the top level block. Now you can see, instead of the Explorer wizard, because this is that's a different tool. Now I am showing you this output, which is a RTL schematic, where A and B are inputs and C, D, E, F, G, H, I are outputs. It has created a block now. It has identified A, B are inputs, C, D, F, G, H are outputs. Now block is gates, type is gates. Now let me click on view technology schematic. When I click on view technology schematic, now you can see this, the main block is there. I'll double click on this. When I double click on this, you can see, let me zoom in. I hope you are able to see now. See, this is the technology schematic, where, let me zoom in to show you one by one. At the top, you will see one inverter. This is that inverter. For that inverter, it has added one buffer at the input and buffer at the output. Always, whenever the code is converted into hardware, always the synthesis tool will add additional buffers, because signal is coming from the external world and signal is going back to the external world, right? So it always adds a buffer so that the input signal will be strengthened and even the output signal will be strengthened. So even though we have not written a code for the buffer. By default, it adds that buffer. Then you can see below, there is this LUT2. Let me double click on this LUT2. You are seeing one OR gate there, right? LUT stands for look up table. I will not tell about LUT here today. In the theory class, anyhow, we are going to discuss in detail about it. Don't worry too much about it. But you can see that here, again, one more buffer, then this LUT. LUT2 corresponds to LUT2 and D1 corresponds to OR gate. Again, LUT2 and E1 corresponds to, let me double click on this. You can see this as a NAND gate. Is it a NAND gate or a NOR gate? Which gate is this? Which gate is this? Which gate is this? Anybody? NOR gate. A bar plus B bar, right? A bar into B bar. A bar into B bar is A plus B whole bar. So this is a NOR gate. Instead of NOR gate, why is it showing AND gate and inverter separately? The reason is inside Xilinx, there is only AND gate, OR gate and inverter. That's all. Inside Xilinx, it can implement AND gate, it can implement OR gate, it can implement inverter directly. If you want other gates, it will connect it this way. Anyhow, the tool is powerful, and anyhow in FPGA there are thousands of gates. We don't have scarcity of gates inside FPGA. So it does not really bother there. The OR gate will not be there. In general, there will be LUTs, lookup tables, and there will be a lot of multiplexers inside FPGA. Using multiplexers and LUTs, it is going to implement the hardware. That is why I say synthesis is a wonderful process where the code is converted into hardware. Now you can see here also it is called as LUT2, here also it is called as LUT2, but the instance name E, right? See this C1, it has given the number itself as D1, E1, F1, G1 and H1, I1. It has purposefully given that way. Why? D1, output D, instance number 1. Similarly, it can create multiple instances. But in our code right now, we have only one instance. That's why it has created only one D1. And this is now NOR gate I have shown you. AND gate. And below, this is what? This is now NAND gate. A bar plus B bar is A into B whole bar. So this is corresponding to NAND gate. Then next we have, what is this gate? Tell me. Quickly find out and tell me. Any answer? We can just look at the circuit diagram and you can immediately tell. No one is telling. It is so simple. It is XOR gate. A bar B plus AB bar. A bar B. And this is OR gate. As I told you, inside Xilinx, always when it is synthesizing, it will use AND gate, OR gate and inverter. So even though we write a symbol separately as XOR gate as such does not exist. XOR gate as such as a single element does not exist. So Xilinx tool will show you, the synthesis tool will show you the equation for that. This is the equation for XOR gate. A bar B plus AB bar. It is putting that exclamation mark there. I0 and I1 are the inputs for the Xilinx tool here. Why it is? Let me show you that window. It is purposefully creating. Let me zoom. You can see this here. Whenever it creates an instance, for that it is giving a name I0, I1 and O. Those are the default names that are present in the library. That is what it is going to take. So you can see here equation not of I0 into I1 plus I0 into not of I1, that is O. It is going to show the truth table and it is going to have a K-map also. So the tool is industry standard, highly powerful tool. Now lastly we have Xnor Gate. You can see this. This is A bar B bar plus AB. You can see this A bar into B bar plus A into B. This is Xnor Gate. You can see the equation here. Then you can see the truth table here. You can see the K-map here. So let me show you the same thing for some other gate. Equation here is A into B AND gate. Truth table, it is 0, 0, 0, 1 AND gate. K-map, it is AND gate, where it is showing 1, 1 as green, all others as red. So this way, you write any HDL code, which is synthesizable within a few seconds or sometimes within a few minutes. If the code is very long, it will take time for it to synthesize. Within a few minutes, it is going to synthesize the whole and it is going to show the hardware in this manner. In today's experiment, we had 6 logic gates and along with an inverter. For everything, it has put a buffer there. You can see for both the inputs, it is included a buffer. It has connected it, and for every output, it has connected a buffer. Now, for this circuit diagram, the Xilinx tool itself will give one more file called netlist file. And in the netlist file, it will mention all these LUT2 instances, D1, E1, F1. All that LUT is already present inside the library, and all these buffers are by default present in the library, and all the nodes are connected by means of the wires here. And it will be one more file called netlist file, and all that netlist contains the requisite logical information. Now the netlist can be directly implemented as a circuit inside the hardware. That is what is this implement design, generate programming file and configure target device. We will be discussing about it later on in our future classes. So I will be ending my theoretical discussion now. If you have any questions, you can ask me. Or else I'll stop sharing the screen, but the meeting will be on. And I hope Richard has created the assignment for today in the Google class. You will have to write today's observation book and you will have to upload it in the Google class.
Yes, sir, it's done.
Yeah, okay. Richard has created the assignment for that. If students have any questions, you can ask me. Or else I'll stop sharing the screen, but the meeting will be on. Whenever you upload your handwritten observation book, you can leave the meeting. What should we write in the observation? Today's code. I have shared already the lab manual with you, right? You will have to write today's code for implementing logic gates. Then the test bench stimuli, at least the part of the stimuli. You need not write the complete test bench. Part of the stimuli that you write, and then you write the RTL schematic. You need not write the gate level schematic which I am showing you, but the RTL schematic which I showed you earlier, that you can write. Only when you write the codes, only then you remember the codes. If you do not write the codes, you will not be able to remember all the codes. Only writing is going to increase your skill, or only when you practice writing, you will be more proficient. That is why you will have to write the observation book. If there are any other questions, you can ask me, or else I will stop sharing the screen. And I'll mute myself. If there is anything, you can always put it in the chat box. I'll pause recording also. Okay, I hope there are no questions. So I will stop recording.